Okay, well, I've been running, unfortunately, on my primary computer, I've been running a whole thing again, and unfortunately, I made a mistake in this initial conditions thing, which is kind of annoying. But I forgot a length in there, so all those didn't run right. But so it goes. I did sneak in this histogram of the closeness centrality. I don't know what it means at the bottom, and I also have a new layered causal graphs in there.
Okay. But the layered causal graphs have a bug in that if you have a rule that goes from something to nothing, it's not going to work.
Okay. Well, I'm sure you'll produce a fix for that. Okay, let me just add something to the to-do list. Which is make a hypergraph option, a hypergraph plot option that makes trivial self-loops smaller, render smaller. I think I have to kill this process on here. Oh my gosh, it just finished. What do you know? Fancy that. I was waiting for it to send me mail. What? What the hell's wrong with that? Well, let's go to that URL. I don't know why that didn't work or why it says it doesn't work. Cloud at the URI, cloud object of this is not valid. I do believe, by the way, that this time I think we might want a different. Should we have more lines on this? Well, I don't know, we can. I do think that it's actually worked this time in terms of having the correct, that these numbers are correct.
You mean deduplication?
Yeah. Look at that nice dimension. I mean, we should probably put the fit underneath, but look at that. That's really nice and flat.
Right.
I mean, that's one of our old manifold ones. I think one of the things we need to do is to find some manifolds and some simpler rules, because I'm sure they exist. Is this rule an exponential grower? Yes,
Yes,
I'm
I
sure it
think
is.
so. Actually, I think it's nested.
Yeah, I'm sure it is. Is it a pure exponential there? Took 1900 to 2230. 3.5 hours. Okay. Huh. It doesn't have a simple linear occurrence. .41, like √2. Well, okay, so I had a couple of things I really wanted to talk to you about. One was the looking for particle-like things in and even string rewriting systems. Okay, so I figure, by the way, we're having some trouble with the multi-way system code. But I figure, here, let's see. If we have a rule that says something like, here, let me show you something. Let me just check that this is working at all. So it's like BA goes to AB. And we have something like, okay, so this So you see this creature here. So I'm going to claim oh, that's really weird. Look at that. Why does that have two separate causal graphs? Let's just look at one particle propagating. And by the way, I wanted to ask you about, I guess we can do, okay, so this is one particle propagation. Okay.
The reason causal graph is disconnected because there is no way to exchange P and C.
Right. Well, okay, so let's look at this thing with its causal graph, full causal graph. It's just, right, that's just the thing tooling across the page. Okay, so in this case here, that's different. Wait a minute. I don't understand. Why are there multiple starts like this here? See what I'm asking?
Wait, is that identical? No, the C is in different places.
But how did the C get to be in different places? I'm very confused. Well, okay, let's look at the states graph here.
Looks like connections are missing because, well, there has to be some events that move to a different place and they're not there.
Ugh, this bug, I don't understand this bug. Let's look at this bug for a second. What's not there?
Well, the events
should
that
be
move
events.
C around.
Yeah, I agree. I don't understand where they are. I mean, they're here in this one, but here. Oh, no, wait a minute. Those are CAA. No, but they're not all CAA. That's CAAA. All right, let's take a look here. We start off, but then we got to understand the states graph thing. What the heck are those disembodied events? Well, let's see. If we have an evolution events graph, that's right. That's completely correct, right?
I think.
So if we go, by the way, my idea, okay, in this case, is to add a rule that says A goes to AA, another rule that says AA goes to A. Maybe we can take out a few of those. Oh boy. Oh, for God's sake. Stop. Oh.
Well, it works. Not that we're going to see anything.
I think it may have a pretty regular structure.
I think it's going to be a big blob.
Just wait. I think it may have a lattice at the back. I'm hoping it has a lattice at the back and then some kind of sign of propagating B's and C's. Come on, render, render, render. Wow. Funky, come on. Anyway, the question is, what is the signature in the causal graph of particle-like propagation? That was my question here. Do you think you know the answer to that?
Not really.
Okay. Well, as a cliffhanger, to see if the whole thing crashes. While it's running, we could just have a quick look. I don't know whether these universes are in the order that we generated them in. I think they may be. Or are they in the inverse order? Up.
Are they sorted by ID in your scene?
I don't think so. Oh, don't say this has got to do it again. All right, I admit this is a big waste of time. I don't know what they're sorted by. Nothing very sensible, I think.
Well, the first page is sorted by ID. No, I think they're sorted by ID. Yeah, they definitely are.
Okay, I admit this is kind of crazy. Let's just go on.
Well, I think the first thing we need to sort them by is the status.
Why? We're going to put our universe
our
first?
universe, yes.
Great.
But more practically, it means that the one we know are not correct are going to go to the end.
I think we have no hope to get that puppy to do anything useful, so I'm just going to delete it.
Let's start with 2 steps. Okay.
Okay, now what happens if we try and layer this thing? Nothing useful. All right, let's try looking at this with only a single B there, without the C. God, what the heck is going on there? Let's try looking at it without. Well, let's try looking at it without the B business at all. Okay, so maybe what we want to do is look at the graph. I don't even understand that graph. Do you? Whoops.
Well, not really, but maybe we can just have it grow, but not shrink to begin with. Probably simpler.
Okay.
Okay, now we can put B in there.
I don't think that's going to be very exciting because I think that what the hell is that doing? What is that doing? I mean, we could do a graph complement to see what the difference is.
Well, everything's different because there's no B in the first one at all.
Yeah, I understand, but I'm trying to get some sense of what would happen in a causal graph.
Do you think we should look at single variable graphs first?
Yes. I don't think we have, do we have the tools to do that for this? We have,
Well, we have the tools of Wolfram model.
yeah, I know, but we have.
And we can easily make
What is it
particles
called?
there.
Sequential order? No, it's not called that. What is it called?
It is just sequential.
Yes. All right, so let's try this one.
Wait, that's different thing because that doesn't do replace all at each step. It just replace in one place.
Yeah, I understand. So really, this needs to be like, oh, that's boring. I see this, the graph is always going to be trivial like that.
Well, I don't know how it sorts them. Why don't we do Wolfram model case?
Okay, how would we do that?
Well, we can put a single vertex edge there, which should be a B, and then we can have it grow trivially, but by having one edge extend the two.
Tell me what it should be. Tell me what the rule is.
Okay, so first is list of 1, 1, 2 goes to 1, 2 list of 2.
Okay, with what initial condition?
Well, just a path graph. Well, I mean, it wouldn't actually take, I mean, path graph is edge list of path graph with list applied on it.
What, I don't remember what path graph is.
Well, it's path 1, 2, 2, 3, 3, 4, and so on. Well, it's not edge list, it's a list applied to it with 3 edges. Well, it's edge list. Okay, it's edge list of path graph and then list, right?
No events.
Yes, and we also need to add a single vertex edge to the path graph. So to append to this list, list of 1. Okay, now it moves around.
Now, what are you proposing to do? So let's just say hypergraph plot. Okay. Cute. Okay. Good work. All right. Now,
Well, now we can make it grow.
is that what we want to do, or we want to have some structure? Think if it's growing at the speed of light, and the particle is moving at the speed of light, and it's not going to end well.
What it means, I'm going to end well.
All right. What do you propose to do? What do you propose to do here? You want to grow it?
1, 2 goes to 1, 2. No, 1, 2 goes to 1, 3, 3, 2. Well, actually, it's possible it would go all the way without it growing. No, actually, no, it will grow simultaneously.
1, 3, 3, 2, like that.
Yeah. I mean, we can make it grow more slowly.
Yeah, I mean, that's just worming. The whole point is that it's going to stick, this thing's going to stay at the end because the worm is just extruding itself. You see what I'm saying? We need it to grow more slowly.
Oh, I see. Okay, let's do, instead of 1, 2 goes to 1, 3, 3, 2, let's do 1, 2 to 3 goes to 1, 2 to 4, 4, 3.
Goes to what? 1, 2.
1, 2 to 4, 4, 3.
I don't understand that. But...
Well,
How did it manage to? Oh, it got to the other end because it moved by 1 step. Even as the space it was living in moved a lot.
Wait, this is 2 steps. Well, yeah.
Okay, let's look at the. Okay, do you understand that? How do we label these things again? In here, do we have a
Well,
way
you
to
can
label?
just do vertex labels option to it. No, you just put after causal graph as a second argument, vertex labels goes to automatic.
How does that help us? I don't understand this at all. Let me try the pure thing without any particle. You know what I'm saying?
I think it has to do with the way it partitioned.
What the hell is that? Well, let's try running it a bit. Let's try making it longer. Oh, for goodness sake. The hell is that?
It's interesting. Well, it partitions itself in different ways. So it just, you know, if it picked pairs of edges in such a way that they're different all the time,
Yeah.
then it would have disconnected pieces.
Okay, what does the layered graph plot mean?
Well, so it partitions into pairs as the first step. Then at the second step, it partitions in a new set of pairs, and some of those overlap, which is how it gets connected, and it keeps doing it.
Okay. All right, so let's insert a particle into this thing. Hopefully it's got enough structure we can see something. So here we say append. And what do we want to append? What level of thing do we want to append? What did we append
Well,
before?
just one, least of one. But we'll put it at the beginning.
Ooh, look at that. Swank.
Does it? Are you sure it has anything to do with the particle?
Well, we'll find out.
I mean, it will only create events if it actually moves.
Yeah, I think it is moving though, relative to the background space. All
Can
right,
you put it
let's do this.
somewhere else?
Yeah, I'm going to put it somewhere else. I'm going to put it somewhere like 5. I think that's our particle, and there's a lot. It's smashed to pieces. See, there is the particle. It's going. There are the pieces of the particle, I think. Or do you not believe that?
What pieces?
Well, I mean,
It's, I'm not sure.
can we do? Is there a graph difference? Yes.
I think after you did a plot on it, it became a graphics.
Yeah. Okay, we can look at this, but you don't understand where the particle is going here, and nor do I. All right, let's try putting it at position 2. See, there does seem to be some difference there, right? Let's take it out altogether. That is the trace of a particle, I think. Now the question is,
so. I mean, there's I think the reason it looks like this is that the density of events over there is a bit larger than elsewhere.
exactly. But I think that's almost the definition of being a particle. Question is, what is the minimum set of events that we need to maintain space, so to speak? And by the way, I'm just to understand what this actually does.
Well, the density is larger because the events are smaller. In other words, if you replace this rule with 1, 1, 2, 2, 3 goes to 1, 2, 2, 3, 3, I'm not sure it will stay this way.
Can we get the background to not grow all the time?
Well, we can just keep it the same.
Then
1,
there
2,
won't
2,
be any
3
event.
goes to 1, 2, 2, 3. Events will still happen.
Let's take a look at that. That's an interesting claim. All right, that's the one without any particles. So let's go like range of 20 there. Okay, I don't understand what that is. Do you understand that? Is that just a glitch in the drawing?
I think so, no.
You don't think so?
No, it isn't.
Okay, what the heck is that?
You
What is happening
this
here?
one first.
So
So
let's number the nodes.
sure, I do understand it. Let's see.
I think it's choosing to do the updates in some very weird order.
How many edges do we have? Can you check?
In what?
Well, path graph 20, there are 19 edges. There's odd number of edges, which means it can pick pairs uniformly. So at some point it picks pairs in a different way because it picks pairs up to 18. Right. And then
There
it
you
has
go.
to use the remaining vertex, so it picks up different pairs next time.
Okay, okay. All right, now here comes a particle. Aha. What the heck is going on here?
Well, particle messes up pairs because particle uses one edge,
Yeah, I
and then the
understand.
pairs are created differently. I mean, we can make size 2 particle. If instead of 1, 1, 2, 1, 2, 2, we have 1, 1, 2 to 3, and 1, 2 to 3, 3.
But I mean, this is like a defect. It's like the propagation of a defect, but how do we show this?
No, no, it's not a defect, it's updating order. It's messes up updating order because it's not a pair. Actually, there is no need for us to use pairs anymore, since it's not growing. We could just have 1, 2 goes to 1, 2 then now.
Okay, hold on. What are you saying?
We don't
What
need
do we-
pairs anymore. We can just have 1, 2 goes to 1, 2. Oh wait, no, actually, no, that's not going to work.
Yeah, because the way it knows there's a particle there.
No, it will know that the particle, but it wouldn't move it because it would always use a single edge rule instead of 2 edges rule.
Well, we could indicate a particle with a self loop or something.
And what difference would that make?
Because then it wouldn't misalign things. Look, if we did this,
Why?
well, I don't know. Maybe I'm wrong.
I don't think it makes any difference. Well, the difference is now second rule can now apply to this particle and update without moving it.
What the heck does that mean? So without the particle, it looks like that. Okay, so then we put in a particle. I don't understand this. Okay, do you understand what it's doing? We put in a particle here.
Yes, I understand what it's doing. I don't understand yet how to fix it.
Wouldn't it help if there was an initial event that all these things came from?
I don't think so. I mean, we know where it would be, what it would look like.
Okay, but what is happening here?
Well, the updating order got missed one edge, and then it, it's moving because of it.
But where's the particle?
Well, the chances are it's not being used at all. Because the second rule now matches everything. Okay, let's see. Well, one thing we can do is to force pairs by inserting some structure every other step. I mean, every other position in the path graph.
Okay, suggestion.
So, for example, you would have 1, 2, 2, 2, 2, 2, 3, 3, 4, 4, 4, 4, and so on.
Wait a minute. 1, 2. What are you saying?
So 1, 2, then the second edge is 2, 2, 2. Or it's even simpler. 1, 2, 2, then 2, 3.
1, 2, 2, 2. What
No,
do you say?
1, 2, 2 is the first edge.
A triple edge?
Yeah. Then 2, 3. Then 3, 4, 4, and so on. So that's going to be the grid. Actually, wait a second. No, that's not what we want. Okay, no, it has to be 1, 2.
Yeah, 1, 2, like that.
Then the second edge is 2, 2, 2. Then 2, 3, 3, 4. Then 4, 4, 4.
I don't understand this bit at all, but anyway. Okay, so you're having even numbers.
Yeah, and now when we update the pair, we update it as 2, 3, 3, 4, 4, 4, 4 goes to 2, 3, 3, 4, 4, 4, 4. This way, they will always have to be the same.
Okay, hold on. So what you're proposing is that this thing is a table of ij, j, j, j.
JK.
No, it's not right. It's I plus 1.
Yeah, right. That's better. Right. Yeah. And then I is, no, it moves in increments of 2. Why do you start it with 2? You can start with 1.
Okay.
Okay, that's a grid. And then, so the particle is exactly the same as before.
As before when?
Well, this single vertex edge, to not confuse things.
You mean this guy here?
Yeah. But
Okay.
then instead of 1, 2 to 3, we have, let's say 1, 2, 2 to 2 to 3.
Goes to the same thing.
Yeah. Yeah, now we don't have any choice of where to pick the pairs.
Okay, well, that's unexciting. So now let's put in a particle. How do we put in a particle here? We say append
Well,
to
just
this.
append one.
Ooh, exciting, exciting. It doesn't know where it is. It has
Well,
no idea
because
where
it's
it is.
disconnected.
Yeah. But if I run it for longer,
Well, you can run it for infinity. It would move. Actually, no. We cannot because network will, I mean, grid will keep updating.
that's nice. Now, well, it's just for the hell of it. I just want to see what it looks like without the layered graph plot part of it. Oh boy.
Well, right. There's a thing that is connecting all the pieces. It's a
Yeah, it's a
particle.
particle, right?
Yeah.
Okay, let's take a look at the actual evolution histories. It's just going to look like a worm, isn't it?
Well, definitely worm with hair.
Let's see how much hair it has.
Well, every two edges it has one hair. By construction.
What the hell are we seeing here?
Wow, this is a grid.
Yeah, I know, but how do we see the particle moving? How do we see it moving?
Well, it didn't move yet, as it appears.
What's that?
That's a particle.
Okay, so let's zoom in on that particle a bit.
Can you just set image size to like 500?
I mean, let's pick one of these up. We'll just see it. But I was thinking we'd just have a smaller grid so we could see the thing. Yeah, there it is. If we really wanted to make it more obvious, we'd make it a bigger bullseye, right? How do we make it?
Well, we cannot right now. But I mean, it's not too hard to make an option for it.
No, I didn't mean that. I mean, just by giving it more self, can't we have it be a larger degree self vertex? If it's a degree,
well, you can put multiple of them and move all of them at once.
No, I was thinking of, can't we have a degree 4 vertex there or something? No.
Well, yeah, we can. Instead of
like?
1, you can use 1, 1, 1, 1.
Right. Instead of 1 here, right?
Yeah. Well, everywhere. This will be 1, 1, 1, 1. Then it will be 2, 2 on the right hand side. And then in the initial condition, it will be 5 or 5, 5.
Doesn't help much. What happened there?
Seems pretty obvious.
What?
Well, that's particle with 3 self-loops.
But how do we make it have a bullseye of a bigger bullseye? What is
well,
that?
We can have multiple multiple single vertex edges would put more circles around it.
Right, which is just more particles, right?
Right.
So, I mean, we could do that if we really wanted to. We could do that by having...
Yeah. It will make it's well, yeah. To make it 6 times slower as well.
Okay. Join that. Yeah, well, it doesn't really help much.
It did help.
Yeah, I mean, it makes it
Well,
bigger.
you can see it now.
Yeah, right. But I mean, I think the other way to make it bigger... Oops. It disconnected. Okay, so this moves every other step, is that right?
Kind of. The last step would move twice. I mean, no, I mean, the last step, it moved every step for some reason.
Okay, what is it doing here? That picture is at least comprehensible.
Well, it obviously has this update in order. Because of the way the pairs are selected and so on.
Right, okay, but there's a particle propagating. Okay, so let's see what the analogous causal graph looks like. So that's frigging weird because...
Why?
Well, it's just, we wouldn't expect. I mean, a particle is what knits, you know, in a sense, it's what knits the universe together.
Well, but that's, well, I guess.
What we expect is that...
That's because the space itself is not knitted.
I know. So the question is, can we do some minimal knitting of space? Like, can we make it just interchange values in space to keep space knitted while the particle goes through?
Let's think about it. How about we add 3/4 to the space? At the end of the self-space rule, we just add 3/4.
Well, this one here.
Oh, at the end there, yeah. This way they will overlap, but will, well, I mean, I don't know how
You put a
well
3/4 at
they,
the end.
yeah. Well, obviously the states are still the same, but well, up to, but the space will update slower now. Can we do it without the particle first?
There's a very small space. Well, let's do a bigger one. That's beautiful. That's beautiful. That's a beautiful shield ladder type construction. Okay, let's do a bigger space. So to make the space bigger, we just append, instead of doing 5 there, we'll do 20 there. Okay, why did that happen? Let me just, out of superstition, let me put a 19 there. Why did that happen?
Well, it's not good enough.
I didn't understand what this was doing anyway. What would happen if we had the 2, 3, 3, 2? 2, 3 like that. And maybe I'm just completely confused, but what would happen if we did 3, 2 here? Great. Why does that happen?
Oh, you broke it. Now it can only update once. The second there's a pairs are messed up, so it's not going to update at all.
Okay.
Well, what if we go back with 2 pairs without any extra hair on them? And just have the odd number of edges.
Okay, 2 pairs here.
Yeah.
Okay, then what?
Well, we don't need that 1-on-1 anymore.
We just need an eye there. What do we have in there?
No, we don't need an eye there. We just 2 pairs. And then we need to have odd number of them, which that actually might not work because they always pairs of them.
What are you suggesting?
We need to keep only one list inside of the table.
Okay.
I mean, we need to go back to our path graph construction.
Well, let's do it by hand though. Table I. What are you saying? You're saying a path graph
I plus 1. Well, okay.
range of 20 or something.
Yeah. And then edge list of that is list map applied to it.
What is that? I don't understand this thing. That's what we had before.
Right. Well, it is knitting, but it's in a weird way.
It's not doing very much knitting. I mean, let's just try continuing this for like.
But it has to eventually. So
yeah, there we go.
What did you do?
I just ran it for a lot longer.
All right. Well, you see one event starts knitting immediately. That's the edge which couldn't find the pair as the first step.
You
But
mean
the rest
here?
of them keep in pairs for different intervals of time. So But
All right,
eventually this edge, which is not in a pair, shifts around.
okay, so let's say we append to this. Now we do see something moving there. I think if we do this one, back. Because the problem is, as soon as we have I mean, in rough terms, look, what we're seeing qualitatively with particles is just additional events that knit together pieces of the space that wouldn't otherwise be knitted.
Yeah. Okay, I have an idea of how the uniform knitting.
Okay.
So if you go back to the haired version, but we move the hair around a bit at each step.
This one here.
Yeah.
Hold on, I just need to get a piece of food. I'll be right back. Just a second. Hi, hi. Yes, you have an idea.
Yes, so we can move this hair around. And the problem is that we will shift and then it works the next time. So we somehow need to move it back and forth. I guess we could have two different kinds of hairs. Yeah, how about so there will be 3 rules.
Okay.
In the second rule, instead of the 2, 2, 2 on the right hand side, you put 2, 2, 2, 2, but not, let's see. But put it at the end. Actually, no, not, it should be 3, 3, 3, 3. Doesn't matter if it's at the
Yeah, it
end
doesn't
or
matter
not.
what order it is.
Right. Well, it matters a bit, but not here. And then the other rule would have, yeah, so just copy this one. It will be similar, but at the input it will be 2, 2, 2, 2. And the output will be 1, 1, 1. So I put it back. So then it should oscillate.
Ooh, look at that.
Okay.
Very swank. Let me just show the rule. Okay. What? It's kind of weird.
Nothing. This rule will get a bit complicated, but you know,
Well,
there might be an easier way to do it.
we can call it network engineering.
Right.
Okay, so let's here, we want to append, what is a particle on this rule? Just a 1 again.
Yeah.
Ooh, lovely. It's odd because here, let's make a layered graph plot of this.
Well, here it decreases density because it prevents other routes from doing things over there.
So gosh,
That layout at the top is really weird. But other than that, yeah, it's pretty clear what is there.
well, actually, hold on. What we really want here is one of these. What the hell is that? What the hell is that? And what's that weird front doing there? look, the basic point, which we already knew, is that the signature of a particle is, a systematic disturbance in the causal graph. By the way, should we try and write in, everything we're doing here, we could perfectly well do for string rewrites where we use the same maximal, maximal updating, right?
I think so.
I think we should have code that does that. I mean, in other words, the string rewriting code, right, we show code that makes the causal graph, as I had in the NKS book, actually, from a maximal rewriting string. Because then some of the stuff will probably be easier to do in the context of strings. Is that easy to write? It should be. We should already have code that's essentially like that inside the multi-write system stuff.
Yeah, I think I did write that code at some point.
Can you try
I
to
think I
find it?
emailed it to you.
Oh, for goodness sake.
Let's see. Yeah, I don't know if it, I mean, I think I did see it somewhere in the source code of multi-write system, but I'm not sure where.
Okay. Well, wait a minute. We just have to do your maximum update thing.
Right. Do you remember how it was called?
Yeah, we called it max. So we have that. Just a minute. So hold on. Okay, hold on. Max scan. Well, let's see if it just
It's not
works.
called that in the email.
I know, but oh, look at that. It does do something. Does this make sense? Look, in the max scan there, I don't understand why it branches at all. See what I'm saying?
Well, branches if events are independent. Wait, what did you change? Okay.
Oh, sequential.
Well, the events are independent. Then it should branch.
But hold on a second. But we want just a causal graph from a single evolution history, right?
Yeah.
But that's not what this is going to do. This has, again, multiple evolution histories, doesn't it?
I don't think so. I think it's one.
Well, why does
Well,
it
it
branch?
has backgoing arrows, which it, I guess, automatically inserts, which are not part of the evolution. But it branches because there are independent pieces of it. Essentially, the causal network is disconnected.
Okay, well, so let's do a, it is true that the causal network says it's disconnected. Okay. So what's the analogous? So let's do our particle. Okay, so our particle is tooling along happily here. And now let's have space be updating itself. What happens if we just do that? Oh my.
Well, it doesn't use the first rule anymore. The second rule is smaller.
So what's your point? Okay,
What about AAA goes to AAA?
AAA goes to AAA?
Yeah. Yeah, then we always prefer the first rule if possible. Okay.
So let's do a bunch more A's there. The hell's that?
Well, I did move once.
Yeah, I mean, I'm sure if we go a bunch more steps, it'll move again. Right, so it's moving there.
Oh, I see. Maybe this. Wait a second. Oh, but because this system doesn't know anything about the age of the nodes. So as long as it moves past the first three A's, it stops moving.
Oh, and it just repeats the A's there.
Yeah. I'm not sure how to prevent that.
Well, I mean, what I did,
have patterns as well.
look, what I did in the NKS book is I just had it do the equivalent of replace all.
Well, it does replace all.
But you say it just gets stuck because it keeps on doing the B. I'm confused by that.
Well, it keeps doing A's because, well,
Why? The B rule is first. It should do it first.
it doesn't do it in the rule order.
Why not?
Well, because it's identical to what I do for Wolfram model.
I see. We should get code. I mean, you think you sent me code that does the pure string case?
Isn't this the code that's used right now?
This here? No.
Yeah.
Because as you say, it doesn't care about rule order. I mean, I've got code in the NKS book that does this, that makes.
Well, I didn't write code that cares about the rule order.
Okay, so I think I need to get the code out of the NKS book that does that, I think.
I mean, you can modify the code we have in the multiway system. It shouldn't be too hard.
Okay.
It's probably a bunch of ifs in some order or something like that.
Well, so what do we want to, I mean, hold on, let me just put this in the to-do list. Let's see, we also want to have, so what are we saying here? We're saying add make the analog by the way, we did have something here that says random updates, right? Look, just I think I'd really like to do is to have a little look for some manifolds. Let's hunt for some manifolds. Okay, we've got a certain distance of particles. We've got some intuition about particles. Let's go hunt for some manifolds. So the question really is, we were looking at the very simplest rules before. In our rule enumerations, let's see here. So some of these we looked at the complete collection, I believe. Like 1, 2 goes to 2, 2. So like here, we know there are no manifolds and 1, 2 goes to 2, 2.
Well, we know it because it has one at the left. Can it have manifolds if it only has one edge?
What?
Actually,
Wow.
let's see. Is that true?
That's not true. Right, but we don't know about for different initial conditions, for example.
Well, surely for one two-vertex edge, it can make a manifold.
Okay, prove it. Do you think it matters what the initial condition is? Or do you think a single edge is enough?
Well, to some extent, but let's see, I'm not sure. Well, let's see.
See, these are all trees, but I have a feeling it seems like there are ones here that should do it.
Which ones are this?
One, two goes to three, two.
I don't see how it can make sense. How can it make anything except for trees?
That's not a tree.
Because it. Which one is not a tree?
This one here is not a tree, nor is that one a tree. Nor is that a tree.
Well, okay, let's understand it.
Yeah, I understand. Okay. So let's pick a one that isn't a tree. Well, here, let's, I mean, I can. Hold on, let's just go. Here, I'm going to clear it and just repick.
Well, yeah, I understand why it doesn't always have to be a tree.
Do you think the initial conditions matter? Okay, so look, this one is definitely not.
Well, there are only, well, let's see. So there are only two initial conditions possible here. That is 0, 0, 0, 1.
Okay, hold on.
Everything else would create causally disconnected pieces.
Why do you say that?
But because single edge on the left-hand side, its causal network is always a tree.
So, okay, but if you have two edges, it could knit things together, right?
No, it can't.
No, I mean, if you have two edges.
Ah, you mean as a rule? Yes,
Yeah.
and it is, yes.
Okay, so
Well, the problem is we don't really know what manifold is in networks.
No, I know, but we know it when we see it.
But that's why I cannot prove it, because I don't know what it is.
I understand. That's why we just have to look for them. Okay, so what is this guy? What do you think that guy is?
Well, it makes triangles, and it's purely constructive. So we've seen these ones before.
No, I understand that, but I mean, okay, fine.
Doesn't seem to be manifold.
That's clearly too stringy to be a manifold. I mean, it's interesting, and I don't understand how it can have the topology it does.
Wait, this one is very simple. It's let's see. Yeah, so what I can explain it to you. So if you remove one of the two threes from the right hand side of the row, you will just get a circle.
Okay.
But now it duplicates every time it adds stuff to the circle, which causes us to branch out.
Okay. Okay, well, I agree that there's probably nothing in this set. Okay, so the question is, do we have to have more on the left-hand side? It's not self-evident. So let's go look for, in the case of 1, 2 goes to 4, 2 is the next case. Let me just label this. This is 1, 2 goes to 3, 2. And do we select for, we killed the pure exponentials here. So we actually don't know in this case. That's a case we haven't looked at then. Okay, there's the 1, 2 goes to 4, 2. I bet we killed the pure exponentials again. Okay, I think we need to look at the exponentials because right, I think it's going to be linear occurrence growth or something. So in this case, oh, we didn't look at pure exponential there. Unfortunately, we have to run that again. That was nice and quick. Oh, God. You don't think a different initial condition is going to make a difference here?
I think it's unlikely. I mean, it could change large-scale topology in this case, but I don't think it can turn it into a manifold.
Nothing. Wait a minute, that was... What did we just do? 1, 2 goes to... 1, 3 goes to... Oh, that's a completely different thing. We just did something completely different. We just did 1, 3 goes to 2, 3. We haven't done 1, 2 goes to 4, 2. Okay, that's 1. Okay, this is 1, 2 goes to 4, 2. Okay, what we need to do here but that wasn't really an adequate number of symbols there. Okay, that's more like it. That's with 10 symbols. Okay, what do you think about the 2 2s? Well, clearly with the 2 2s, we're getting all kinds of connected sea creatures.
Well, that, I mean, I don't see any reason that could not produce a manifold.
Right. And there, the initial conditions will probably make more of a difference.
Yeah, they might.
So the minimal case is then 2 2 goes to 3 2, right? Okay, let's take a look at these.
I guess.
Those are very generic trees. But you see, even this guy is more interesting than we're getting from the... Why haven't we seen that one again at 1 2 goes to 4 2? See what I'm saying?
Yeah, they're choosing them at random.
What's that?
I mean, we don't enumerate. Wait, are we enumerating all of them?
Only for small number of symbols. So I think we want to do a bigger case here. Yeah, you know, that's the thing we're missing here, because that was an exponential.
I mean, it's very easy to make one with 1 2 goes to 4 2 case.
Make a what?
Make one that look like that, which you just showed.
Okay, tell me how.
Well, you just add another edge on the right hand side, which is, you know,
Oh,
there is
to that
duplicate.
one. Yeah, to
Right.
that one. I understand that. Okay. So I'm just doing all the 1 2 4 2s since they were mostly exponentials. Okay, what do you think about trying? Do you think a different initial condition is going to be totally irrelevant?
I'm not sure.
Oh yeah, let's try one more set.
Well, in that case, I don't see
Yeah,
how it would help.
I can't see how it would help because I can't see how it could knit across anything. I doubt that guy's going to be interesting, but let's just pick him out. I'm going to give that one a chance. Did we use the right number of symbols here? Okay, what is that thing? I'm not sure we've seen one like that before. We'll at least add it to our collection of interesting ones. Okay, but that's definitively not very manifoldy. I mean, it's interesting. It's lovely and decorative, but not manifoldy. Okay. So did we use enough symbols here? 10 symbols. Is that enough for these?
Let me see. I think it's too many actually.
Okay. Well, let's run your symbol tester. Do we need to run it, or can you do it by hand?
Well, it's better to run it. Very reliable.
Do you remember what the thing is called? Do you remember what it's called?
Not really. It's max connected atoms.
Six. Okay. Oh, look at that guy. Look at that guy. I really need a thing that just does a That's promising. That first one is somewhat promising. What do you think? It's not totally thrilling, but it's not completely trivial either.
But it doesn't look like manifold to me.
No, it's not a manifold. I like it though. It's an interesting object. I mean, I like these ones that have a small number of, yeah. Okay. I don't think we should give up on this set yet. I think we should try another set, yeah. Actually, you know what I should just do for these ones? We should just do if we just use graph plot, we can do it a lot faster. A nice centrosome. Okay, what's that again? That's another one of those ones with a lot of centrality.
Yeah, it is the same one.
You think it's the same one?
Well, up to orientation, yes.
Okay. All right, well, should we do, let's look now at the 2, 2 goes to 3, 2. Do you agree?
Okay.
And what do you think the maximum is there? Well, let's just go look. Can you go compute it? Let's see, 2, 2 goes to 3, 2. And this might matter what the initial condition is. 6. Okay. You know what? I want to rewrite a couple of these things so that they're faster. Those are completely boring. Well, yeah, I think those are completely boring. So probably what we want to do is to pick out. Oh, I mean, we just need the ones. We need to pick out some of these. Okay. Which way around does match Q work? I want to say match Q thing and then pattern.
Expression and then pattern.
What's that?
Expression and then pattern.
Okay. How can we be getting disconnected ones? Oh, that's a different one. Okay. Just run it again. Do you think this can be nothing? Okay, we probably need to try some other initial conditions here. Nothing. All right, let's see what happens if we try a different initial condition. 6 is the right number. Is that right for this? 2, 2 goes to 3, 2?
Let me check. Yeah, 6.
Wow, there are very few rules that are bi-connected. It's interesting. Oh God, all of these things. Oh no, WMF filter doesn't care about that. Okay, what initial condition should we use here for the 2222 case?
Well, I mean, I guess we could try 1, 1, 2, 3.
What is that?
1, 2, 2, 3. Well, okay, sometimes they don't evolve at all.
Shit. What's this doing? I wonder if that's because parallel map monitored is inside another parallel map monitored.
Yeah, I don't know what that is going to do.
I don't see why that should be. What is that? Why is that? Okay. Well, it's odd, but not harmful. So why is this buggy? I don't understand that. Do you see why this is wrong? What? What the hell is happening here? Hale, help me. Help. What is
I think we've
happening?
seen it before.
What's that?
I think we've seen it before.
Yeah, I think we've seen it before as well.
The second warning is from the function repository.
Okay, so these are all failing.
Right.
Okay, let's see if what happens if I just say 1, 1, 1, 1 here. I get perfectly good results.
Well, most rules don't match 1, 2 to 3.
Okay. So how do we tell which ones do? Why don't we just have 1, 2, 2, 3 on the left-hand side?
Yeah, we can.
So let's see, how do we do that? If we want to have, so we're going to have 3, 2 on the right-hand side. So we might as well just do a table of up to 6, right? Random integer, 1 to 6. Ah, now we got this thrown around. 3, 2. Okay. 1, 2, 2, 3, arrow. And now we're going to make a table of 50 of those. And we're going to select by connected rule queue. Okay. Boring. I'm surprised that there's no pure exponential here. Or is that obvious? Okay, everything here is a tree. So what about a different initial condition? Is that useful here or not?
I'm not sure.
Let's try something. So what else can we try?
Maybe I guess I could try 1, 2 to 1.
Yeah, why not? That was suspiciously fast. Wow. Found absolutely nothing. Found nothing. Let's try it again. Most of those died quickly. So what about yeah, there's nothing there. Okay, so what about another possible what about what would happen if we had, is it obvious what will happen if we have a what can we have that would be an interacting thing, like 3, is this crazy? 3, 1, like that?
Okay.
Oops, that's not what I want. I just want, oh, I made a mistake here. I didn't want that. I wanted over on the right, I want 1, 2, 2, 3, right? I don't want 1, 2, 2, 1 in the rule.
Right,
I only
the
want
rule.
it in the initial condition. Much livelier. Much livelier. Got some life in those animals. Very tree-like. Everything's a tree or a circle. Well, let's just try the 1, 2. Let's try that triple there. This thing looks like it's sticking out its tongue at us. But none of those look very manifoldy. All right, got any other ideas here? So what about, is there anything that we could do on this rule here? Well, you know what, I'm going to go to the 4, 2 case. 2, 2 goes to 4, 2. And what do you want to do with the initial condition here? 1, 2, 2, 2, 2, 3. Let's try that first. Let's just remove the pure exponential to begin with. Ooh, look at that guy. That guy looks interesting. That one looks possibly interesting. Possible. That one looks interesting. It's getting closer. None of them are quite it, but it's definitely getting closer. What about that one? I think we've seen ones like that before. Oh boy. Okay. What do you think here? Are we I mean, I wonder what happens if we try the same things with
I don't know, that last one is not a manifold.
well, let's take a look. What about that one there? I mean,
It's kind of, I mean,
all right, let's look at that one in more detail. That's hopeless. What about that guy? All right, let's look at this last one. I'm not optimistic, but we'll look at it further. Hairy animal, but I'm afraid that's not a manifold. Shaggy. I just want to see whether it grows from a 1, 1, 1, 1 initial condition. That's actually a bit cleaner, maybe. Exactly the same shagginess. Replace it now. I just want to look at the other ones there and see whether they are affected by having a simpler initial condition. Not a whit. They couldn't care less. They just couldn't care. All right, what's your next idea for what can make a manifold? You think we should try some hypergraphs?
I guess.
I
mean, I don't really know what is that?
I don't know why it should take a hypergraph. So let's see. We've got, let's see, we're doing here 2, 2 to 4, 2. I feel like some of these are almost rands. So do you think the left-hand side, 1, 2, 2, 3, is a fertile left-hand side? Do you think there's any point on any other left-hand side?
Well, 1, 2 to 3 just means merge anything. Well,
actually, I want to try, wait a minute, I didn't try the pure exponential here. Hold on, I didn't try pure exponentials. There are 108 of those. I mean, I don't think there's going to be anything here. I think they're all going to be trees. Let's take a look. What the hell? What's that guy? All right, there's two possibles here. Does parallel map monitored Curry?
No.
That one's kind of nice, but it isn't. See, look, what we had, these other ones, we had a lot of symmetry in them. The ones that we know make manifolds from the old trivalent graph stuff. And they couldn't care less about the inertial conditions yet again.
I mean, we could try to look at this, trivalent ones in more detail to see what exactly do they do to make manifold.
I think that would be useful. I mean, I think that one, because we know, I mean, I think that they fill in, they're like generalized Sierpinski-like things. Okay, so first of all, these, it has not helped us to have non-default initial conditions. However, okay, hold on. We are getting some non-trivial things in this. Okay, so there's no reason to have that. But that's worth having. Okay, let's do this. Don't know, maybe it'll be, but is it obvious that something like that is hopeless?
No, it's not obvious.
Well, that guy is interesting looking. That is some kind of twisted Sierpinski. I think we've seen a bunch of those before. And that one isn't really interesting. That second one is mildly interesting. These feel very close, though. They feel close. It feels like we're not that far away from making.
Yeah.
I mean, just one of these could suddenly do it. Now, Actually, for these, we could select. I don't think we care about the ones that are disconnected. So we could not show those. Just edit, make pictures too. What is the connected? What is the way of testing whether a graph is connected?
Well, it means just connect the graph Q.
That's what I wanted. What? Oh. Ooh, look at that guy. Oh, look at that. Look at that thing. That looks promising to me.
Yeah.
That's quite promising. Now, let's see.
But if he starts with 1, 2 to 3 initial condition.
I'll try it. Does that look very different to you?
Well, it has some ends to it, but not very different. Oh, actually, I don't know. Maybe not.
I don't think it's that different.
Yeah.
Boring. Okay, let's do a bit of a bigger run. That's our only hope. I think we've seen a bunch of those before. Is that any different from what we've seen before, do you think?
Doesn't look like it.
Let's keep it anyway. We should wrap soon. But getting this left-hand side like that is very fertile. I mean, maybe we should just have a little look for some 5-2s. Do you think there's any point in going to a 3 thing on the left-hand side?
Well, I mean, I think it might help with manifolds, I'm not sure.
Let's just check that one. I don't want to be lazy here. All right, let's try, you want to try 3 on the left. So we're going to be trying 3-2 goes to, should we try 4-2 or should we try, do we want to, yeah, we could try 3-2 to 4-2. How many, what's the size of the symbols for that? 3, 2,
8.
Okay, so I'm going to try 1, 2, 2, 3, 3, 4 on the left. You agree?
Okay.
Try the that thing like that. Let's try 1,000. Thrilling. Boring. Okay, let's try 3-2 to 5-2. Just and the size of the alphabet there. 3-2 to 5-2 is 9. Great. That's uninspiring. Why is this failing so much? Is it because that left-hand side is unfertile for some reason? Do you suggest a different left-hand side of the rule?
Well, maybe we could try 1, 2, 1, 3, and 4, which you did before.
1, 2, 1, 3, 1, 4.
Yeah.
Why is that dead? Just does nothing. Why are these dying so much? Okay, I don't understand. Do you have any idea why this is happening? Let's see what most of them are doing.
I'm not sure. I don't know what is different compared to what we were doing before. I mean, we looked at this left-hand side quite a bit last time.
Yeah. But they were doing okay. Wait a minute. Wait a minute. There are cases here that say may be interesting, but it wasn't picking those up. Okay, hold on. Let's try this again. Okay, what's wrong with my code here? Pure exponential, or maybe interesting, or linear recurrence growth. Close for the match queue. Okay, what is wrong here? Oh, 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 oh. Let's try and look at this. What the hell? That thing with the connected graphs was going wrong somehow. How can these not be connected?
Is it, does it have anything to do with directions, maybe?
I bet it does. I bet it does. I bet it does. So actually what we should probably do here, all the way back up here.
Yeah, connected graph 1, 2 to 3 is false.
Okay. All right. So I have to say undirected graph here, right?
Yeah.
All right, we should think about how we explicitly test for manifoldianism. I mean, we could test dimension, could test for not a tree and dimension. Okay, there are a lot that look a lot like things we've seen before. That one looks mildly interesting, although I think we've seen ones like that before. I doubt that one is interesting, but let's give it a chance. That's like the head of Aries. It's a rather nice looking one. I think we've seen a lot of these before. That second one is the only one I really care about here. I think that one's quite nice. It's a lot of the same kind of stuff we're seeing over and over and over again. I don't think these are particularly interesting. But, okay. You probably fell asleep on me. Yeah.
Yeah, I don't need to go to sleep.
Yeah, so do I. All right, to fight again tomorrow. I might as well start a run here while I'm at it. Right. Okay, I'm gonna start another generation run. I wonder whether we should have more than 6 on a page, because I can change the I can change the number of things on the front page. Like, I don't know why that doesn't go back to the main thing, but on here, if we want to change the number of rows and columns, right? We got 6 rows. What do you think? Do you think we should go down to more columns? I think we should go to like 8. You know, I think we should have more on the page. Do you agree?
That really depends on the monitor size.
Okay.
So we cannot really decide that. I mean,
well, I mean, it does that. You see.
Yeah, I understand, but the pages are the same.
Right. Well, at least for my monitor, I'd like more. I'm gonna get like.
So on my 15-inch MacBook, this is pretty much ideal because it just fills most of the screen. But I guess, I mean, I imagine using like iMac or something like that, in which case it probably be not enough.
I think it's okay to have to scroll down. We'll put a navigator on the page. We'll put a separate navigator on the page, I think.
Do we actually need pages?
I think only for loading. I think it doesn't work very well to load. Okay, pagination 3. I'm going to put 8 there. Oh God, I have to actually redeploy this. Okay, here goes.
I think the correct way is to put as many as it takes to fill the largest reasonable monitor, and everybody else will just have to scroll.
Yeah, I understand. Okay, here goes. We're going to blow them away. Actually, we could have tried that 8 thing before we did that, but too late now. Okay, we are now up to 280. Let's just try the first one. Just to check we're not totally wasting our time. And then off we go. I think I found a few duplicates actually as it ran before. You know, we should actually build a test environment so that we don't have to do this thing about blowing everything away. See, this makes something like a manifold, doesn't it?
Well, that's normal Sierpinski. I mean, it's kind of manifold, but it's
Oh, God. Why didn't that work? Hold on, I want to get this to
if
work.
it does find duplicates, why do we need to delete everything every time?
I guess we don't. That's a good point.
I mean, obviously, we cannot just keep doing it after it's public.
What is this doing? What is this doing? Okay, I'm going crazy here. Let's go back to look at this. Notebook template. Okay. Look, I have the word length in there. Do you see that? I have that word length in there. Now
Yes.
I go back here and I go up here and I say deploy universe template files. Notebook template. Actually, let me do this. Let me go to that place. Let me see what it looks like. Oh, thank you. That's just crazy. That's just crazy. I just ran the thing. Okay, hold on. I don't understand how this didn't work. How could this not have worked? Do you see this code here?
Well, I see it. I don't think I understand it.
Okay, that is correct. Now that's also correct. I don't understand. Well, it should now work. Let's see if it overwrites. I have a bad feeling about this, that line is taking forever. That after all this trouble we've gone to, yeah, I think that grid thing is not working out. Oh, that's really annoying. Oh God, don't say it's not interruptible. That's super annoying. Rat. I see. Come on. Don't hang. Come on, just run. Why is it taking so long? All right. Well, anyway, look, I'll see you tomorrow. This is silly for you to watch this too.
Okay.
Okay. See you later.
See you.
Bye.
Bye.